Chapter 6.4, Solving Trigonometric Equations Using Identities. Solving trigonometric equations means determining all the possible angle values that make the equation true within the given domain. When the domain is not restricted, provide a general solution. When a trigonometric equation involves more than one trig ratio, use identities to rewrite the equation in terms of a single ratio by using one or more of the following: reciprocal identities, quotient identities, Pythagorean identities, sum difference identities, double angle identities. Once the equation is rewritten in terms of a single trig ratio and set to equal 0, use algebra to simplify the equations in order to determine the solutions. Remember to check that solutions for an equation do not include non-permissible values from the original equation. You can always verify your solutions graphically. Example: solve each equation over the domain x is greater than or equal to 0 and less than or equal to 2 pi. The first one is 2 cos x plus 1 minus sine squared x equals 3. When we see 1 minus sine squared x or 1 minus cos squared x, we should think of the Pythagorean identity, which says cos squared x plus sine squared x equals 1. So if we subtract sine squared x from both sides, we would get cos squared x equals 1 minus sine squared x. So I can rewrite 1 minus sine squared x as cos squared x. Then we would have 2 cos x plus cos squared x equals 3. I can subtract 3 from both sides and put this in descending order of degree. So I have cos squared x plus 2 cos x minus 3 equals 0. And then I can factor this trinomial. We want two numbers that multiply to negative 3 and add to positive 2, which would be 3 and negative 1, 3 and negative 1. So the trinomial factors to cos x plus 3 times cos x minus 1, and that equals 0. Then we look at each factor, and when is it equal to 0? Cos x plus 3 equals 0. Subtract 3 from both sides, we get cos x equals negative 3. And cos x minus 1 equals 0. Add 1 to both sides, we get cos x equals 1. Cos x equals negative 3, that's not possible. Cos and sine are always between negative 1 and 1, so not possible. Negative 1 is less than or equal to cos x, which is less than or equal to positive 1. Our other factor, cos x equals 1, when does that happen? Cos is the x value on the unit circle. The x value equals positive 1 here at 1, 0. So that is at 0, and when we go all the way around, it gets back to 2 pi, and our domain is greater than or equal to 0 and less than or equal to 2 pi. Therefore, x equals 0 and 2 pi, and we don't have any non-permissible values since we didn't have any fractions. So those are our solutions. Sine 2x plus sine x equals 0. I can't factor this because it's not 2 sine x. 2 sine x is different from sine 2x. So I can't factor this because this angle is different from this angle. So in this case, I have one trig function, but I actually want to change it to something else. So sine 2x, I can look at my formula sheet and look for the double angle identity of sine. double angle identity for sine 2a is 2 sine a cos a. Then we can rewrite this as 2 sine x cos x, and then plus sine x equals 0. Now I have a common factor of sine x in each term, so I can factor that out. Sine x times 2 cos x plus 1 equals 0. And then I can look at when each factor is equal to 0, so sine x equals 0 and 2 cos x plus 1 equals 0, which means 2 cos x is -1 and cos x is -1/2. When is sine x equal to 0? Sine is the y value. Y equals 0 here at the point 1, 0, which is at 0 and 2 pi. And sine also equals 0 here at the point -1, 0, which is pi. So between 0 and 2 pi, sine x equals 0 when x equals 0, pi, and 2 pi. And then cos x equals -1/2. Cos is the x value, -1/2 is here. So that would be at this angle and at this angle. Those would be reference angles of pi over 3. So theta 1 would equal pi minus pi over 3, which equals 3 pi over 3 minus pi over 3, which is 2 pi over 3. And theta 2 equals pi plus pi over 3, which is 3 pi over 3 plus pi over 3, which gives us 4 pi over 3. So in one rotation, cos x equals -1/2 when x is 2 pi over 3 and when x is 4 pi over 3. We don't have any non-permissible values because we didn't have any fractions. So x equals 0, pi, and 2 pi, and x equals 2 pi over 3 and 4 pi over 3 are the solutions for this problem. Cos squared x minus 3 sine squared x equals 0. I can rewrite cos squared x in terms of sine squared x as 1 minus sine squared x using the Pythagorean identity. Then the expression becomes 1 minus sine squared x minus 3 sine squared x equals 0. I can combine the like terms. I have -1 sine squared x and -3 sine squared x, which gives me 1 minus 4 sine squared x equals 0. This is a difference of squares, so I can factor that. It becomes 1 minus 2 sine x times 1 plus 2 sine x equals 0. And then I look at each factor and when that's equal to 0, so 1 minus 2 sine x equals 0 when 1 equals 2 sine x by adding 2 sine x to both sides, then divide by 2 and we get sine x equals 1/2, and 1 plus 2 sine x equals 0. Subtract 1 from both sides, we get 2 sine x equals -1. Divide by 2, we get sine x is -1/2. So we're looking for when sine x is equal to positive or -1/2. Sine is the y value in the unit circle. So 1/2 and -1/2 are here, which means we would have angles in all of our quadrants. The reference angle is pi over 6. So theta 1 equals pi over 6. That would be a y value of positive 1/2. Then theta 2 would equal pi minus pi over 6, which is 6 pi over 6, minus pi over 6, which gives us 5 pi over 6. So for sine x equals positive 1/2, we get x equals pi over 6 and 5 pi over 6. And then for sine x equals -1/2, our third angle here, theta 3 would equal pi plus pi over 6, which is 6 pi over 6 plus pi over 6, which is 7 pi over 6. And then our biggest angle, theta 4, equals 2 pi minus pi over 6, which is 12 pi over 6 minus pi over 6, which equals 11 pi over 6. So for sine x equals -1/2, we have x equals 7 pi over 6 and 11 pi over 6. And again, we don't have any denominators, so there's no non-permissible values to check against these. Sine squared x equals tan x cos x. We can write this as sine squared x equals tan is sine x over cos x, and then times cos x. Can divide out the cos x, and then we have sine squared x equals sine x. Move everything to one side by subtracting sine x. We get sine squared x minus sine x equals 0. We can factor out a sine x to get sine x times sine x minus 1 equals 0. And then we look at each factor. When is sine x equal to 0, and when is sine x minus 1 equal to 0, which is when sine x equals 1. So when is sine x equal to 0? That's the y value when y is equal to 0, which is here at 1, 0, which is at 0, and also 2 pi. And here at -1, 0, which is pi. So sine x equals 0 when x equals 0, pi, and 2 pi. And then when is sine x equal to 1? The y value is equal to 1 here at the point 0, 1, which is at pi over 2. So sine x equals 1 when x equals pi over 2. This time we do have a non-permissible value because we have a fraction sine x over cos x. So cos x cannot equal to 0. When does cos x equal 0? Cos is the x value on the unit circle, so that is here at 0, 1, and also here at 0, -1, so that's at pi over 2 and 3 pi over 2, so we cannot have solutions of pi over 2 or 3 pi over 2, which means we cannot have x equals pi over 2 here, because this is a non-permissible value. So our solutions are 0, pi, and 2 pi. Solve sine squared x equals 1/2 tan x cos x over the domain x is greater than or equal to 0 degrees, less than or equal to 360 degrees, and verify your answer graphically. We can write our equation as sine squared x equals 1/2 times tan x is sine x over cos x, and then times cos x. Then our cos x's divide out, and we have sine squared x equals 1/2 times sine x, which is sine squared x equals sine x divided by 2. We can multiply both sides by 2 to get 2 sine squared x equals sine x, and then subtract sine x from both sides to get 2 sine squared x minus sine x equals 0. Next we can factor out a sine x. Sine x times 2 sine x minus 1 equals 0. Then we want to look at each factor and when it's equal to 0. So sine x equals 0 and 2 sine x minus 1 equals 0, which gives us 2 sine x equals 1, so sine x equals 1/2. When is sine x equal to 0? That's when y is equal to 0 on the unit circle. So at this point, 1, 0, and at this point, -1, 0, which is at 0 degrees and 180 degrees. And then when we get all the way back around, it's at 360 degrees. When is sine x equal to positive 1/2? Sine is the y value. That gives us a reference angle of 30 degrees. So first one is 30 degrees, and the second one would be theta 2 equals 180 degrees minus 30 degrees, so 150 degrees. We need to check for non-permissible values. We do have a fraction here because we have tan, so cos is a denominator, which means cos x cannot equal 0. When is cos x equal to 0? That is at 90 degrees and 270 degrees. So x cannot equal 90 degrees and 270 degrees for this domain. And those were not any of our answers, so that's fine. So sine x equals to 0 when x equals 0 degrees, 180 degrees, and 360 degrees. And then sine x equals 1/2 when x equals 30 degrees and when x equals 150 degrees. And then the question says to verify your answer graphically. Y equals, clear what you have in there. And we can enter sine squared x for the first equation, bracket, sine x, move out of the bracket, and then squared. Our second one is 1/2 times tan x cos x, enter, graph that. Need to make sure that I am in degree mode for this question. Mode, I'm in radians, change that to degrees, enter, exit, y equals, graph. I want to change my window. I want a domain from 0 to 360. And maybe I'll count up by 30. And then my y values just from -1 to 1, counting by 1, graph that, and this is what we get. So we have, it looks like 5 intersection points in this domain. We have one right at the beginning at 0, we have one here, we have one here, we have one here, and we have one right at the end at 360, which is the same as what we had here, 1, 2, 3, 4, 5. So let's just double check what those are. Second trace number 5, enter, enter, enter. Okay, it's giving me an error. I'm going to try changing my window to just go a little bit further left, so maybe -10, and then 360, just so it's past the point where the intersection should be. Let's see if that helps. Second trace number 5, enter, enter, enter. Okay, well, again, this graphing calculator app is having issues. So with my graphing calculator, I first make sure that I am in degree mode for this question. y1 equals bracket sine x close bracket squared, and y2 is 1/2 tan x cos x. I graph that over a window of 0 to 360, counting up by 30, and y values from -1 to 1, counting by 1. And then F5, find my intersection points. I have one at 0, 0, it tells me. The next one is at x equals to 30. The next one is at x equals to 150. The next one is 180. The next one is 360. So that verifies all of my solutions that I had algebraically solved for. Determine general solutions. Algebraically solve the following and give a general solution in radians. Cos 2x equals cos x. Cos 2x, let's go to our formula sheet and find the identity for cos 2x. So cos 2x, we have a few. I'm going to write it in terms of cos so that my equation only has cos. So I'm going to write cos 2x as 2 cos squared x minus 1. Equals cos x. Then bring the cos x over by subtracting. We get 2 cos squared x minus cos x minus 1 equals 0. And then we can factor this. It's a complex trinomial, so multiply 2 times -1, which is -2. We want two numbers that multiply to -2 and add to -1, which would be -2 +1, -2 +1. Then we use the box method. We have 2 cos squared x. In the bottom right, we have -1. Then we have -2 cos x and 1 cos x in the other two boxes in any order. And then common factor each row. 2 cos squared x and -2 cos x would be 2 cos x. Cos x and -1 would just be 1. Then 2 cos squared x and cos x would be cos x. And -2 cos x and -1 would be -1. So the trinomial factors to 2 cos x plus 1 times cos x minus 1 equals 0. Then we look at when each factor is equal to 0. 2 cos x plus 1 equals 0 when 2 cos x equals -1. So when cos x is -1/2 and cos x minus 1 equals 0 when cos x equals 1. When is cos x equal to -1/2? Cos is the x value, -1/2 is here. That gives us two angles. Our reference angle would be pi over 3. So angle 1 would be pi minus pi over 3, which is 3 pi over 3 minus pi over 3, which equals 2 pi over 3. And angle 2 would be pi plus pi over 3, which is 3 pi over 3 plus pi over 3, which gives us 4 pi over 3. And when is cos x equal to +1? That would be here at the point 1, 0, which is at 0 radians, and then again at 2 pi radians, and etc. So we have three principal angles. Our general solutions would be x equals 0 plus 2 pi n, where n is an element of the integers, and x equals 2 pi over 3 plus 2 pi n, where n is an element of the integers, and also x equals 4 pi over 3 plus 2 pi n, where n is an element of the integers. And we didn't have any fractions, so we don't have to worry about any non-permissible values. 3 cos x plus 2 equals 5 secant x. We can rewrite this as 3 cos x plus 2 equals 5 times 1 over cos x. We have cos x in the denominator, so we're going to have an NPV with cos x cannot equal to 0, which is x cannot equal pi over 2 plus pi n, where n is an element of the integers. We'll continue simplifying. We can multiply both sides by cos x. Then we get 3 cos squared x plus 2 cos x equals 5 times 1 cos x over cos x. These divide out. And then move the 5 over, we get 3 cos squared x plus 2 cos x minus 5 equals 0. We can factor this. Again, it's complex trinomial, so 3 times negative 5 is negative 15. Two numbers that multiply to equal negative 15 and add to equal 2 would be 5 and negative 3, 5 and negative 3. Use the box method. First box is 3 cos squared x. Last box is negative 5. The other two boxes are 5 cos x and negative 3 cos x. Common factor each row and column. 3 cos squared x and 5 cos x would be cos x. Negative 3, negative 5 would be negative 1. 3 cos squared x and negative 3 cos x would be 3 cos x, and then 5 cos x and negative 5 would be positive 5. So our trinomial factors to cos x minus 1 times 3 cos x plus 5 equals to 0. And then look at each factor. Cos x minus 1 equals 0 means that cos x equals 1. And 3 cos x plus 5 equals 0 means 3 cos x equals negative 5. So cos x equals negative 5 over 3. Negative 5 over 3, that's a number that's smaller than negative 1. So that's not possible. Since cos is greater than or equal to negative 1 and less than or equal to positive 1, and negative 5 over 3 does not fit within that domain. So our solution is just going to be when x is equal to 1. X equals 1 here at the point 1, 0, which is at 0, 2 pi, 4 pi, etc. So our general solution would be x equals 0 plus 2 pi n, where n is an element of the integers, or just 2 pi n, where n is an element of the integers. Three sine squared x plus cos squared x equals 2. I can rewrite one of these trig functions as the other using the Pythagorean identity. I'm going to do cos squared x. So cos squared x, using the Pythagorean identity, we have sine squared x plus cos squared x equals 1. If I subtract sine squared x from both sides, I get cos squared x equals 1 minus sine squared x. So then I can write the equation as 3 sine squared x plus 1 minus sine squared x equals 2. Then I can combine my sine squared x's. I have 3, take away 1, so I have 2 sine squared x plus 1 equals 2. Move the 2 over by subtracting. We get 2 sine squared x plus 1 minus 2 is negative 1 equals 0. This is not a difference of squares because 2 is not a perfect square, so I can't factor it. Instead, I'm going to isolate the trig function. So add 1 to both sides to get 2 sine squared x equals 1. Then divide by 2 to get sine squared x equals 1/2. And then square root both sides. But we don't know if sine x started as a positive or negative, so we have sine x equals positive negative 1 over square root 2. And if we rationalize the denominator by multiplying by root 2, we get sine x equals plus minus root 2 over 2. We don't have any NPVs because we don't have any fractions, so we don't need to worry about that. We just need to determine what the x value is for sine x equal to positive and negative root 2 over 2. Root 2 over 2 is a reference angle of pi over 4. We have sine equals positive and negative root 2 over 2, so that's in all 4 quadrants. And we have that each of those angles will be 90 degrees away from the last one, or pi over 2 away from the last one. So the first one is pi over 4. The next one will be pi over 4 plus pi over 2. The next one will be that one plus pi over 2. The next one will be that one plus pi over 2. So then our solution, general solution, is x equals pi over 4 plus pi over 2n, where n is an element of the integers. That brings us to the end of the Chapter 6 notes.